In the previous video, we've looked at how you would convert a regular expression into an NFA using McNaughton's-Yamada-Thompson's algorithm. And so now what we want to do is we want to convert this non-deterministic finite state acceptor into a deterministic finite state acceptor. So why would we do that? Well, a DFA is more efficient on speed, like time-wise, because it won't need to try and compute every single possibility and then realize that, oh, there is no answer. So a DFA will only have, so it'll have a unique state for each other state. So in this case, for B goes to C with epsilon, and it goes to D with epsilon. That's non-deterministic. We want to make it deterministic. So one way of doing that, or I guess the way that I'm going to teach today, would be the epsilon closure. So epsilon closure basically requires you to calculate all the possible nodes once, so all the possible states from a state that it can go to. So for example, let's find the epsilon closure of A. So A can go to itself with epsilon. So epsilon is basically the lack of something, like the lack of character, so do nothing. So that means, I'll just put it in curly brackets, A can go to A to itself, and by definition, a state can go to itself in epsilon closure. So it can go to A can go to B with epsilon, so we also include B, and then we'll include B can go to C with epsilon, because from A we can go to C, so from A we can go to D by just having epsilons. A can also go to H, sorry, this is 1. This is 1 or 0 star 1 NFA. A can go to H with epsilon. And that's it. Then let's calculate the epsilon of every other state. So one thing to note is that let me tell you after we find epsilon of B. So epsilon of B would be to itself always. Then it can go to C. You see how there's a 1 here? With epsilon, it can't go anywhere else. B can go to D. There's a 0, so it's blocking the epsilon, so it can't go there. So it'd just be B, C, D. So let's calculate the epsilon of C. You see how the epsilon of C is only C? So there is no arrow pointing epsilon, only to itself. So we can basically, for these closures, we can actually just erase this. Any epsilon closure that gives us 1, that gives us just the starting state, is basically just ignored because we won't need to calculate it. So epsilon of D would be the same thing. With epsilon, it can only go to itself. We ignore that. And let me just skip a few states, so E, F, G, and let's just go to I. Epsilon I also can't go anywhere but to itself. So we scratch that out. Now, let's go to H as well, epsilon of H. It can only go to H. So we scratch that out. Now let's go back to E, F, and G. So E, epsilon of E. Epsilon of E. So from E, you can go to E, G, H, A, B, C, D. So let me reiterate. From E, you can go to G, then H, just because it's an epsilon trail. And you can also go to E, G, A, B, C, E, G, A, B, D. So we're just going to combine all of that. So we'll find the union of them. And it must be unique. So you won't repeat it. So it'd be E, G, H, A, B, and D. E, G, H, A, B, and D. A, B, C, and D. C and D. Now let's find the epsilon of F. It would be F, G, H, A, B, C, D. Now let's find the epsilon of G, which is G, A, B, C, D. Okay. And one thing to note is that, yes, we are finding the epsilon closure of every state, but in our final deterministic acceptor, once we try and graph this, we'll realize that there's a lot of optimizations that can be done. And basically, we can ignore some of the states because you won't be able to ever get to it, but yet it has like states that go back to the DFA. So it's basically, if I have an NFA with A, and it goes to with 1 to B, but then let's say this is the starting state, start, okay? And let's say this goes to with 0 to C. And let's say it's a finishing state. And let's say with 0, it goes to C. So you see how we start at B, and with 0, we go to C. So our regular expression here is simply 0. However, you see how the state A, there is no way of getting to it. So an optimization of this NFA would be just simply removing this because there is no way to get to it. So that's what we're going to have in our case with these epsilon closures, is that lots of optimizations can be done. Okay. So let me scroll down, and I will need to do this. There you go. So we have the graph in our view as well. So what I'm going to do is I'm going to create a table. And I'm just going to, I guess I'm going to create the table over here. I'm going to call it phi. Kind of looks like a null, but we can ignore that. And I'm going to say with 1, so the whole alphabet 1 and 0. And I'm going to use all of the closures in this table and any possible finite state that we're going to get from the resulting closures in the graph, in the table. So let's start with the closure A, B, C, D, H. A, B, C, D, H. So the way you would compute it is you would look at the graph of the NFA, and one by one for each state of this whole state. So this is in our DFA. This is going to be one state. So A, B, C, D, H is just going to be one state. But while computing the DFA, we kind of treat this as one state, but also we must compute them separately. So basically, let's look at state A. Can state A go anywhere with 1? No. So we ignore that. B, can B go anywhere with 1? No. C with 1? Yes. Now here's something to note. Because we went somewhere with 1, that means all the future epsilons after going somewhere with 1 or with 0, for example in our case, will be considered. So for C, the answer is it can go to E, G, H, A, B, C, D, because it went through 1, therefore it can go through all epsilons. You can't do it the other way around. You can't go through an epsilon, then 1, and say, go through epsilons. That doesn't work. You must go through the state, then you can go through all epsilons. So from C, we can go to E, G, H, A, B, C, D. E, G, H, A, B, C, D. Now, C is considered. D, D with 1? No. H with 1. H with 1, yes. H with 1 can go to I. So bring an I. So now we did all of the states here. And now we have a complete new state that wasn't seen in our closures. which will be in our DFA. So now with 0, we look at A, no. B, no. C, no. D, yes. D can go to F, and then all the epsilons after. So it can go to F, G, H, A, B, C, D. F, G, H, A, B, C, D. And then H with 0 can't go anywhere. So now what we're going to do is we're going to put in the table our new states. So these are new, E, G, H, A, B, C, D, I. And see how E, G, H, A, B, C, D, I is a different state to E, G, H, A, B, C, D. We'll do the ones that appear here, and then we'll bring in these, and I'll explain why some of these states, some of these closures, won't actually be useful for our DFA. And what we can actually do is if our table here doesn't actually produce these closures, then you might as well, I don't think you can, but you might have a hint of certainty that some of these closures won't be in our DFA. But let's look into it. Let's brute force kind of this approach, just computation, 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 and then we can have some of these realizations in our DFA. So let's do E, G, H, A, B, C, D, I. And so we look at E with 1, no. G with 1, no. H with 1, yes. I. A with 1, no. B with 1, no. D with 1, no. A, B, D. I with 1, no. C. This is our last one. C with 1, yes. So it's E, G, H, A, B, C, D. H, A, B, C, D. And here's another thing to note. You see how these states have the same initial NFA state thing? So basically E, G, H, A, B, C, D, I, E, G, H, A, B, C, D, I. It's just not ordered the same. Well, in our case, they are considered the same. So what I'm going to do actually is I'm going to remove the I, and I'm going to put the I at the end, just so it makes it clear to me that these are the same states. Now, this state can go to with 0. So we already calculated that E can't go anywhere, G can't go anywhere, H can't go anywhere with 0. A can't, B can't, C can't, I can't, D can. And as we know, D with 0 is F, G, H, A, B, C, D. So as you can see here and here, these are the same states. So now I'm going to put in the graph F, G, H, A, B, C, D. H, A, B, C, D. And what I'm going to do is I'm going to say F, G, H, A, B, C, D. Going to try to find if any of these states from our NFA go somewhere with 1. F doesn't, G doesn't, H does with I, so I'm just going to put maybe I at the end. I'm going to hope it's going to match with this. It might not though. So H is done, A is done, B is done, D, nope. So it's E, so C here, E, G, H, A, B, C, D. E, H, A, B, C, D. Aha, these are the same. Fantastic. Then with 0, it can go to, so with E, F, G, H, A, B, C, D, C is here, H is here, so that would be, so I can actually remember it's C, E, G, H, A, B, C, D, I. A, B, C, D, I. There you go. And you can see that all of these states here are actually filled in here. Therefore, we won't have to put them in the table. And I actually am not 100% sure, but because our graph here doesn't actually have these closures, then you can actually just ignore these closures. But what I'm going to do for demonstrating purposes is I'm going to actually just fill them in anyway, just so you can actually see it. So I'm actually just going to have a double line here, and I'm going to say keep filling it in. So I'm going to try fill in BCD. BCD. BCD with 1. So B can't go anywhere with 1, D can't go anywhere with 1, and C can go to E, G, H, A, B, C, D. G, H, A, B, C, D. So let's do it with 0. D can go to F, G, H, A, B, C, D, E, D. This is a D. And notice how this is different. This state, E, G, H, A, B, C, D, is different to E, G, H, A, B, C, D, I. Difference, okay? Then, since this is different, we actually have to fill in E, G, H, A, B, C, D, which is, so with 1, it would be, so from C, you can go to E, G, H, A, B, C, D, I, because C and H are the only states with actual 1s. And as we know, C and H, we've already computed C and H above here for A, B, C, D, H. So we can just copy this. E, G, H, A, B, C, D for 0. As we know, 0 is only D, so we only consider D. So whenever there was a D, there was a D here, so we just have this state, F, G, H, A, B, C, D. So this is, I guess, a way to minimize computation for us humans and as a computer. So now we have what? What do we have? E, G, H, A, B, C, D. I think all of these states here have been filled in on the left side of the phi. So now I guess we can cross this out. That's done. That's done. That's done. E, G, H, A, B, C, D. That's done as well, because it's here. F, G, H, A, B, C, D. F, G, H, A, B, C, D is here as well, so that's done. And then G, A, B, C, D. G, A, B, C, D. G, A, B, C, D. Well, as we know, with 1, C and H can go somewhere. This doesn't have a H, so C. And because C was, because we can actually use the BCD here to calculate it. So C with 1 is E, G, H, A, B, C, D. G, H, A, B, C, D. Then G, A, B, C, D. Then D, D, F, G, H, A, B, C, D. F, G, H, A, B, C, D. Now, we don't need the graph anymore, and we don't need the closures because that's also done. That's also done. So what we're going to do is we're going to just graph it. So we're going to have our starting state here, and I'll just say start. So and just before I keep drawing it, I'm just going to say, I'm going to just refer to the NFA as well. Because our NFA had I as our finishing state, any new state that has I, so this, I'm going to put a star here, this has I, that is going to be finishing as well. And the DFA can have multiple finishing states. Okay? So we have a start. So now we don't need to reference the graph, the NFA anymore, but we do need to reference the table. So we'll actually just keep the state. We'll say A, B, C, D, H. That's going to be the name of our first state. And then with one, it goes to a state called E, G, H, A, B, C, D, I. So I'm simply reading the table. And because it includes I, just like our NFA, this must be a finishing state. Right? A, B, C, D, H goes to F, G, H, A, B, C, D with 0. F, G, H, A, B, C, D. with 0. This does not have an I, therefore it's not finishing. And EGHABCDI goes to itself, just reading off the graph here, with 1. And with 0, it goes to the state, 0. And then reading off the graph, FGHABCD, with 1 goes to EGHABCDI, and with 0, it goes to itself. So let's do BCD. Well, there is no obvious way how BCD is connected to any other one here. So I'm just going to put it maybe, I'll scroll down because this is already computed. Boom, we've done this, we've done this, we've done this. So I'm just going to remember phi 1, 0. Yeah. So I don't know how BCD is connected to here. So I'm just going to say, I'll put BCD here. BCD. Maybe it'll eventually be connected, surely. So it goes to EGHABCD. Well, that differs from EGHABCDI. So what I'm going to say, it goes to, with 1, it goes to EGHABCD. And then with 0, it goes to FGHABCD. FGHABCD goes here with 0. So actually, I'm just going to put the 0 above just to be consistent. 0. Then EGHABCDI. EGHABCD goes to here. I'll move the arrows so it's more clear what I'm trying to do. Here with 1. And FGHABCD with 0 goes here. Now GABCD, we aren't really sure how that's connected, so I'm just gonna say, I'm just gonna put it here. GABCD with 1 goes here, and with 0 goes here. Notice how maybe I should change the color. I'll try. Color palette red. Okay. Notice how start node. So I'll color this. Start node can go here. It can go here. And it can go to itself. So it can go to itself. And it can go to itself. And they can go here, and I can go here. Well, can it go? How are we supposed to get to these states? Well, there is no state in here that tells us how to get into here. So these are actually optimizations for our DFA. So what I'm gonna do is I'm gonna cross this in red. Don't care about this, don't care about this, don't care about this. And then I'm going to say all of these scribbles here can be our little optimizations. So what I'm trying to say basically is, because this graph initially didn't produce one of our closures, we do not actually need to fill in the rest of the closures in our graph. If that makes sense. Okay, so what I'm going to do is I'm going to bring back the black color. And what I'm going to do is I'm going to say start node A, B, C, D, H with 1, with 0, E, G, H, A, B, C, D, I, to itself with 1, with 0, with 1, F, G, H, A, B, C, D, with 0. this is our DFA. DFA equivalent of our NFA from above. Same thing, except in this case, our DFA has less states. That's great. It isn't guaranteed. And most of the time, our DFA will actually have more states. So it'll take more memory for a computer, but it doesn't have to compute every single possibility because it's deterministic. From one state to the other state, it only has one possible option with the given character. So with one, it can only go to one state. It's deterministic, so it's very fast at computation. So what I'm going to do is I'm just going to rename the states. I'm going to say start state. I'm just going to say A. So A, B, C, D, H becomes A. With 1 and 0, you can go to B and C. With 0, with 1, with 0, with 1, finishing. There you go. And this is how you'd convert an NFA into a DFA. Thanks for watching.